Hey guys, Mr. Betts here. I want to take a look at a couple of optimization problems that are pretty straightforward. And then in the next video, we're going to look at some more complicated optimization problems. Regardless of the complexity of the problem, we're going to follow those 5 steps that I talked about in the introduction video. So in this problem, we have a farmer that wants to build a fence to enclose a pasture. He has a certain amount of materials to build the fence, and we want to know how does he make the pasture as big as possible. So the first thing we want to do is we want to set up a model. And part of this is introducing variables. And also in this particular example, part of this is going to be drawing a picture. So the pasture is going to be a rectangle. So I'll draw a rectangle. And we're going to introduce some variables here. So we don't need to be too formal about this, but I'm going to call the one dimension of this x, and I'm going to call the other one y. And so we know x and y are going to, well, we know certain things about x and y. We're going to be able to use those to find the area of the pasture, but we're also going to use those to figure out what kind of restrictions we have based on how much fencing we have. So I've got my model, I've got my variables. I also want to determine what kind of values those variables can have. So x can't be just any number. In this particular problem, x can't be less than 0 because we can't build negative length of fence. And also x can't be bigger than 50 because if x is 50, we're going to use all of the fence along this segment and this segment, and we're not going to have any left over for the width. So it wouldn't make sense to do it, but we could build a pasture that just has 2 lengths of 50 meter fence right next to each other, and it's going to have 0 area, but it is a possibility. We could do it. The restrictions on y are going to be the same. Y is going to have values between 0 and 50. And it's important that we understand what values these variables can have so that we get an answer that makes sense later, and we can also restrict our analysis to just this range. So the next thing I want to do is I want to write a function, and I want to write a function for what it is I'm trying to maximize, which is the area. So I'm trying to maximize the area of the pasture, so I'm going to write a function for the area of the pasture. And in terms of the 2 variables I have here, it's going to be x times y. So I can find the area. If I know what x is and I know what y is, I'm just going to multiply them together. Unfortunately here, the area depends on 2 different variables, and calculus gets pretty complicated when we have more than one variable. So we're going to try to narrow it down to just one variable. And we can do that using the equation that's given to us, or we can write an equation at least, using this 100 meters of fence. So the maximum perimeter of this pasture is going to be 100 meters based on having 100 meters of fence. And obviously, if we're trying to maximize the area, we're going to maximize the amount of fence that we can have. We're not going to use less than what we have available. So we're going to say that the perimeter is 100. Well, the perimeter is going to be 2x plus 2y. And since that's equal to 100, I can use this equation to get a relationship between x and y and eliminate one of them from our area equation. So I'm going to solve. It really doesn't matter which one. So I'm going to solve for y. And if we solve for y, y is going to be 50 minus x. So I subtracted the 2x divided by 2. We get 50 minus x. And now I'm going to take this relationship here and plug it into that equation right there for y. So I'm going to rewrite that equation as a equals x times 50 minus x. And for the purpose of actually doing calculus, I'm going to distribute that and get 50x minus x squared. So we can find the area of this pasture right here, knowing just what x is, because we know that whatever x is, y is going to be determined, and we can figure out what the area is. Now what we want to do is figure out what are the possibilities, the possible values for x that will give us the maximum area here. So to do that, we're going to take the derivative. So I'm just going to call it a prime. We could also write it dA dx. Okay, it doesn't matter if you use prime notation or Leibniz notation. We get 50 minus 2x. Then we want to find critical values here. So we're going to figure out where the derivative is either equal to 0 or undefined. This derivative is never going to be undefined, but it is equal to 0. So we get a critical value at x equals 25. So we know then that the maximum area is either going to be when x equals 0. Hopefully it doesn't make sense that would give us a maximum area, but that's a possibility. When x equals 50, and then when x equals 25. So since we are on a closed interval for a function for the area that is continuous, we can use the candidates test. So let's find the area at those candidates, a of 0, a of 50, and a of 25. If we plug 0 in for x into the area function right here, we're going to get 0. If we plug 50 in, we have 50 times 50 minus 50 squared, which is also 0. Both of those I hope make sense, that if x is 0, then y is going to be 50 and we get an area of 0. If x is 50, then y is 0 and we get an area of 0. And then if x is 25, then we're going to have 50 times 25 minus 25 squared. And that ends up being 625. So that value is going to give us the maximum area. We want to make sure that we answer the question though. So if we go back and we look at what the question is, the question says, what dimensions should it be to maximize the area of the pasture? So the dimensions that we're going to use will be when x equals 25. Okay, so the maximum area will occur when the pasture is 25 meters. Make sure we include units by, and then if we plug 25 into this equation right here for x, we're going to get 25 for y. So 25 meters by 25 meters. Now, the last step here says justify with calculus. I've actually done that, and I've done that using the candidates test. I don't have to say that I'm using the candidates test here, but I have used the candidates test as I went through. So I restricted the domain of x to a closed interval. So I checked the endpoints at 0 and 50. And then I also found critical values on the interval, and I checked the area at that point. So what we're doing there is using the candidates test, and we found the area at each of those possibilities, at each of those candidates. We could have also done this justification. I'm going to back up here a little bit and get rid of this. We could have also used the first derivative test because the first derivative has that special circumstance where the derivative is only going to change signs once. So I'm going to look at that real quick. We're going to make a sign chart here for a prime. X values are going to be restricted from 0 to 50. So I don't want to make a number line here for a prime that goes beyond those, because the values of the derivative don't matter outside of that. And I'm also going to put the x value of our critical point on there. So if I plug a number in between 0 and 25 into the derivative, then I'm going to get, let's say I put in the number 1 into the derivative, we're going to get 50 minus 2, which is 48. It's positive. And then if I plug in a number bigger than 25 into the derivative, plugging in here, we're going to get a negative. And since the derivative is always positive to the left of 25 and always negative to the right of 25, then that means that 25 not only is a local maximum, but also a global maximum. So if I were doing this, I would actually need to write it out. So the candidates test, the work is your justification. When you're using the first derivative test, we're going to say something along the lines of, we get a max area at x equals 25 because, and then we would say the derivative is always positive to the left of 25 and always positive to the right of 25. So we need to give that first first derivative test justification if we're going to use a first derivative test. Okay, this problem I'm going to go through a little bit more quickly. It's a very similar problem, but the setup's a little bit different because now we have one side of our pasture bounded by a creek. So we're going to have a creek flowing along here, and then the 100 feet of fence only needs to make up 3 sides of our pasture. So I've got my picture. I'm going to write a function for the area because we're trying to maximize the area. Let me go back to the first step. Sorry. This time x is going to be on the interval from 0 to 50 still. Y is going to be on the interval this time from 0 to, if x is 0, y is actually going to be 100. So y could be as big as 100 and no less than 0. Now I'm going to write an equation for the area, which is going to be x times y again. Again, we want to get rid of one of the variables. This time the equation we're going to use for perimeter is going to be 2x plus y equals 100. I'm going to solve that for y and get y equals 100 minus 2x and plug that into our area equation, and we get area equals x times 100 minus 2x, or 100x minus 2x squared. Okay, now I want to identify candidates, so I'm going to take the derivative. So we get 100 minus 4x. I want to know when that's equal to 0. And so we get a critical value at x equals 25. So we actually have the same critical value as we did on the last one. I'm going to use the candidates test again. If we can use the candidates test, that generally is a little bit easier with our work. And since we're on a closed interval, we can do that. I want to mention again, I want to warn you again that oftentimes the restrictions are going to be an open interval. So even either an open endpoint or maybe unrestricted, so goes from like 0 to infinity. And in that case, we can't plug in infinity as an endpoint, so the first derivative test is generally going to be our only option. In this case, though, the candidates test does work. So I'm going to plug all of our critical values in. Since a is in terms of x, I'm looking at this domain here. So a of 0, a of 50, and a of 25. If we plug 0 into the area function, we get 0. If we plug 50 into the area function, we get 0. If we plug 25 in, we get 100 times 25 minus 2 times 25 squared. So that's going to be 50 times 25, so that's going to be 1250. So based on that, again, at the endpoints, we get the area of 0 like we expected. It wouldn't make sense for our farmer to build a fence that looks like that, but it is a possibility. So we want to answer the question again. The max area occurs with dimensions 25 meters by, and then if we plug 25 in to this equation right here for x, we can get our y value, and that's going to be 50 meters. So I do want to point out here that it does matter which dimension is 25 and which one's 50. In the previous example, 25 by 25, it doesn't matter if x is 25 or y is 25 because they both are. So it does matter which one is x and which one is y. So it might be useful to answer the question a little bit more specifically. I also want to point out that logically, the x value cannot be 50 and the y 25, because then that would require 125 meters of fence, which we don't have. Generally, a question will be a little bit more specific, so it might say what is the length of the side perpendicular to the creek or something like that. But as far as the calculus goes, again, the justification with calculus, we use the candidates test, so this work right here is our justification.